Hello, everybody. This is Andy Ellicott from Swarm. Thank you for joining us today to learn about Columnstore indexing best practices in Postgres. For those of you who are new to Swarm, just a quick introduction. We are in the business of making Postgres go faster and based primarily in Berlin, but also Boston. And primarily the way we make Postgres go faster is through the development of the Swarm 64DA extension for Postgres. And in a nutshell, or at a high level, what Swarm 64DA does is accelerate the Postgres query engine by implementing more efficient join algorithms, enhancing parallel processing, much greater parallel processing, and more efficient query planning, statistics, and things like query costing, things like that, all of which really help the Postgres perform queries, around anywhere from 5 times to 60 times faster, depending on your use case. But in the TPCH, which is a popular data warehousing benchmark, Swarm 64 helps Postgres run about 20 times faster overall, which is great. One of the ways today our agenda is to really drill down into one of the acceleration techniques we employ, which is Columnstore indexing. And with me to explain that in detail is Swarm 64 solution architect Sebastian Dressler, joining us from Berlin. Our agenda is to start with a quick primer on Columnstore indexing basics, and then I'll turn it over to Sebastian, who'll talk about best practices, just kind of like best scenarios to use Columnstore indexing, how to optimize compression, latency, and index latency, table coverage, things like that to help provide the best performance. And we will conclude with Q&A as we go along. Feel free to enter questions in the question panel here and GoToWebinar. And since it's one of the most popular questions we get, I'll answer will the slides and a recording of the event be shared? The answer is yes. Probably within 24 hours, you'll receive an email with a link to the slides we're presenting today, as well as a recording of the event. So you can share it with others or watch it offline. Okay, so quick primer on columnar storage. Columnar storage, and I'll go through different ways that's implemented into different databases in a moment, but that generally is going to provide you with much faster query performance. And with faster query performance, it allows Postgres users to do more with Postgres, right? Mainly migrating projects from Oracle or SQL Server that use, say, the Oracle's in-memory column store feature or SQL Server's column store indexing feature. So those projects can be migrated to Postgres and achieve the same kind of performance, and basically the same way. Also helps existing Postgres databases support larger numbers of concurrent users, get the same kind of or faster query performance on bigger databases for more concurrent users, or to handle more complex queries as your requirements evolved. Also allows you to build databases that support mixed workloads, or sometimes known as HTAP, hybrid transaction analytic processing. It's a fancy way of saying just more queries and analytics on your transactional tables, often used for real-time analytics. And then lastly, it opens up data warehousing projects, which are typically not a sweet spot of Postgres, but with much faster querying. Again, it allows you to use Postgres for data warehousing, data marts, and so on, analytics instead of costlier legacy databases. So if we look at columnar storage, let's first look at row-oriented storage. I assume you're all, as database technologists, you're all pretty familiar with this, but kind of conventional practice has always been to take a logical table, as you see here on the top, and when physically writing or retrieving data in a row, that's done in one movement. right? By storing all of the columns that are associated in a single row together in a physical block or page on disk. Okay, so updates, deletes, lookups are all very efficient because just simple single read to the disk to get or write to get or update that information. But that's a little less efficient, quite less, that can be less efficient if you are querying, right? So if I'm trying to find all of the rows in my table of pets that are dogs, right? I'm really focused on the pet type column, but to look at all of those, the elements in all of those columns, I've got to read the entire row. So there's a lot of waste, right? Unnecessary I/O, reading all of those blocks just to get a single field from each block in my example. Okay, so that's where column-oriented storage came in, kind of really became much more famous, I guess, and conventional and popular in the beginning of this millennium, back in probably around 2005 when Vertica and a little later MemSQL and PowerXL and a bunch of column databases joined. I think Sybase was already in the market with one. But what they did was just kind of rotated the physical storage 90 degrees. And instead of grouping all of the elements in a single row together and within blocks or pages on disk, they grouped the elements of a column together, as you see here. So in a single read of, say, page 1, I'm getting nothing but pet types, right? So if I'm selecting rows based on pet type, just looking for dogs, I'm going to go through this row much faster with about, in this example, 20%, about 80% fewer less I/O than I would have had to have done in the row-oriented storage. So very well suited for querying by reducing I/O. Also grouping similar data items together like this, all the elements of a single column, lends itself very well to compression, and Sebastian will talk about that as well. So there's even greater I/O reduction that's possible with compression. The cost, though, is generally slower updates, okay? Because to maintain the index takes a little longer, or the column storage takes a little longer, just to generally speaking, and that's why a lot of the column databases, a lot of the kind of rocket science in them is figuring out how the quickest way to reduce that latency between, kind of data being updated in a kind of logical row-oriented view, but on disk, or in storage, kind of get that columnar representation. Okay, and Sebastian will talk a little bit about how we handle that. Before I turn things over to Sebastian, want to let you know there are different ways to get columnar storage. Okay, really the first, as I mentioned, kind of about 15 years ago, we saw a rise in the number of columnar databases. These are pure column databases like Vertica, MemSQL, which I think is now SingleDB, renamed themselves. Even Redshift, which is based on a large part on a columnar database called PowerXL, Amazon Redshift. These are, data is just natively columnar storage, right? So very fast query performance. Kind of the drawbacks is that they all tend to be commercial, so they're quite costly. And thirdly, very often they are set up as kind of a second database for analytics. So the source database is, so if you have a transactional database and so you're using Vertica as your analytic kind of view on that to support query intensive workloads, you're kind of duplicating storage or setting up ETL to move data between your transactional sort of system of record and your system of insight in the columnar database. Okay, second option is instead of a columnar database, is to do columnar tables, right, using a special storage format. This is actually the way earlier versions of Swarm worked. our columnar representation was stored in a foreign data table. It wasn't until about middle of this year that we implemented that as a Columnstore index, which we'll explain in a minute. But other kind of columnar storage solutions for Postgres also use the foreign data wrapper, like Citus Data is one of those. Again, fast querying. Now you're getting lower cost because they're kind of originating within the open source community and for open source. You still have the data duplication, okay, even with the foreign data wrapper. A lot of times, the data is being kind of transactionally, the source system is a base Postgres table, and you've set up some trigger or ETL to move the data from the base table into the foreign data table. Also, the foreign data table, a little bit harder to administer since quite a lot of the Postgres tooling isn't built to support foreign tables. So there would be a little bit of extra administrative work you'd have to do, things like backup and restore, monitoring, and things like that. Okay, so the third option is columnar indexes, and as I mentioned before, this is what Oracle and this is the approach that Oracle and SQL Server took. SQL Server implementing Columnstore indexes, which are really what the Swarm 64 and Postgres Columnstore indexes are modeled after. Oracle, their in-memory Columnstore, similar thing, but it's a way of creating a kind of a fast query path into your base table, right, without having to duplicate your base or source tables for analytics. So you get the benefit of the fast query performance. In the Swarm case, low cost, right? Because we're just extending free open source Postgres. And the really nice thing is, just from an administrative and a development standpoint, it's nice just because you have single source, right, same base table, and reducing the amount of data duplication, ETL, and kind of administrative work you'd have to do to gain this fast query performance. Okay. So although easy, right? There are the column-oriented storage and the Columnstore index. There's still questions about how to get the most benefit out of it, right? Like, for example, which tables are best suited, which column, how many columns do I index? What type of columns should I index? There are different kind of compression choices. There are also considerations on, kind of table coverage versus index update, kind of index latency. So for that detail and best practices around that, I am going to turn it over to Sebastian next, and he will go into that detail. Let me just give him the presenter. And there we go. Sebastian.
Thanks, Andy. Welcome, everybody. I'm just setting up my screen share. And as you can guess from the shared terminal, we are going to do parts of this live. So we are on a server we have here in Berlin sitting with Swarm 64DA installed. And now for the agenda, as Andy already pitched it, we cover some of the generic pieces, as said, in terms of what should you index, what are the practices and semantics around that, followed by an overview of choices for compression. And then we will dive a little bit deeper. I have prepared a couple of examples here to basically show you where are some benefits, what are possibly things you want to avoid, and then also how we see that, let's say, the index is updated if you have a more OLTP-like workload coming in, but you do some analytical queries around this. All right, so let's get this started. First things first. So a couple of things in general. What Andy already said is we have added this columnar storage index in terms of adding a very powerful feature to Postgres to enable OLAP queries on Postgres itself. Previously, we have chosen the route of the foreign data wrapper as well, much like what Citus is doing basically. But this in the end has certain shortcomings, especially if you want to keep your data in a relational context, so to speak, or in like an OLTP context, because in our previous versions, there were simply no such things as, for instance, unique keys, primary keys, and foreign keys. We had hints, but nothing was really enforced. So the point here is simply that you gain something. In that case, you could do larger queries, do them really fast, but you also lost key capabilities of Postgres, or you had to recombine things, for instance, by creating a trigger-based ETL or ELT chain in that case, where your foreign data wrapper-backed table for analytics is always updated in a real-time fashion, basically, or at least in a close to real-time fashion. And this is changing now with the Columnstore index, because as every other index in Postgres, it just integrates much better in the ecosystem, and therefore you can benefit of all the features the native Postgres tables are providing you. However, as with all these things, there are some downsides, and sometimes it's a bit, you need a bit to consider certain things to understand when to use something or not. Now, the basic thing about the index is we try to make this really simple from a usage perspective. And if you consider using a entire columnar database, you're probably never going to ask yourself that question, how is my data stored? You just create a table, and all you get out of it is a tabular view, basically, but you're not concerned with the storage part, right? Now, in Postgres, the very same example holds. I mean, in the background, you kind of know this is a row-based storage format, and you possibly know its drawbacks, but that's it. You just create your table, you dump your data, and then at some point, you maybe hit a limit or you don't. Now, when it comes to indexes, this gets slightly more involved, right? Because like if you have a standard B-tree index in Postgres, you really want to consider what are you indexing. Yeah, so if you have, let's say, a single ID column, and you always know that your queries are going to touch this ID column, then the choice is clear. You put an index on that ID column, or the same goes for timestamps. However, the moment you're using multiple columns at the same time to do your queries, your indexing becomes much more complicated. Why? Because if you're using two columns, you want to have a joint index ideally over those two columns. If you're using three, you maybe want to expand your index over the three columns, and so on and so forth. However, this comes at the downside of not being able to very efficiently query a single column again. And this might lead to doing things like creating multiple indexes to span all the varieties you can think of. And this can be very counterproductive, because you also have to maintain these indexes, and they also slow your transactional workload down typically. Now, with the Columnar index, you just look at the table, and there is basically a very easy decision to make. And that decision is ideally you just take all the columns. So if we look at a table here, which is called PartSup, which is short for part supplier. So this table is from the TPCH benchmark on the machine where we are on. There is such a benchmark deployed, a data set with 100 gigabytes of base data. And given the RAM of the machine, so this is roughly 380 gigs of RAM, this workload basically fits in the RAM. So just for information, when we later do some queries, I will probably do them once or twice, two times at least, possibly, to just fill the caches. And then we can also look at the disk IO so that you see that this is cached, and then get a direct comparison to what the index would be doing. And so this is one example table. And if this is your table in production, with these 5 columns here, and you want to use the Columnstore index, then you just go straight ahead and you create the index over all your columns. And that's it. Yeah, you don't have to think too much about these kind of things. And for most of the cases, this is absolutely sufficient. So long story short, you have a table, you want to index the table, you call create index, give it a name, reference the table, and then the key piece here actually is to call using Columnstore, because this is the index name or extension supplies. And then you just go ahead and list all the columns. You can do certain optimizations if you want. For instance, one optimization that might be sensible to do here is to just spare this PS comment column, because possibly with this kind of workload, it is very unlikely that you ever query the comment for something, or nor that you need it. If you need it, then this is maybe a really rare occasion. So this would be one opportunity to save some space or not. But in the end, since this is also compressed in the background, you don't add so much overhead. Now, so far, we have now looked into the index creation. Here's just the syntax again. This is really standard SQL syntax. Create the index, reference the table. Don't forget to say using Columnstore, and then just list all your columns. Now, there are some exceptions we have to talk about. And that is basically what you can take away as a rule of thumb is, if in doubt, just take all the columns. Don't care, just take them all, unless you know what you're doing. So you exactly know your queries are not going to touch specific columns. Then you can just spare them. Like, that is just what we talked earlier about in this example with the comment column. If you know for sure that you don't have any query in the mix that's going to use this column, then just forget about the column, save some space. But if you're unsure about this, rather include it. Doesn't hurt too much. Now, the other limitation, and this is actually a Postgres limitation, unfortunately, is that you cannot have more than 32 columns in that index. And that's a bit more difficult. So we know of certain cases where people like to have really wide tables, and wide meaning here not only more than 32 columns, but we have seen tables with, let's say, hundreds of columns, like 150, maybe even 200, because they serve a very specific purpose. You maybe have then a lot of null values inside your rows, but the problem here is that you cannot simply use them, or you cannot apply the simple logic of just use all the columns, because there are simply too many. And to get around this, you can start to split your indexes. So of course you can create multiple of these spanning different column sets. However, you need to know what your query is doing again, because the moment you accidentally hit a overlapping set and your queries or like your columns are covered by 2 different indexes, then Postgres is likely to choose a table scan. It's definitely not going to choose the Columnstore index scan. Maybe there are other indexes in your system in that case, which it can make use of, but yeah, something you need to be really aware of and careful. In that case, also possibly rather think about whether you can change your schema slightly to just reduce this huge amount of columns. And maybe you, like a common trick here is to just introduce, let's say, a type ID column with an enum on top where you can filter for, and then just have some more generic values, maybe at the expense of having to cast them, which is typically less expensive than keeping so many columns at once. So that's basically one of the main limitations when it comes to creating your index. And this is also the only exception where you have to really think about what you are going to do with this index. Otherwise, as said, just take all the columns. And like any other index in Postgres, this index also works with your existing indexes. It's not simply going to overwrite them So let's say you have traditional B-tree indexes on your tables defined for instance, point lookups, then if you're defining this index on top, it does not mean that you're suddenly always doing Columnstore index scans, but due to the cost system of Postgres, you are going to actually get the best possible operation in your plan. And that's something I can show you later, where we have an example where it was quite difficult to get the, or to tell Postgres to use the Columnstore index. And of course, this works with all the consistency features I mentioned earlier. So if your native tables are having, or if you're making use of primary keys, unique keys, foreign keys, like everything you want to have for consistency, this is guaranteed to be in place, because at the end of the day, this is just an index on top of your data. And Postgres is still responsible for maintaining the integrity of your data according to the constraints you defined. And that's, by the way, some shortcoming of this foreign data wrapper approach, because if you're choosing that route, you have to put these implementation details into your foreign data wrapper. Postgres is not going to take care of that for you, because it does simply not know how your data is accessed in that case and how to ensure this consistency. And that's why it's really difficult to get this in working there. And the choice is pretty obvious here, because you just rely on Postgres doing its thing, and it's known that it does this very well, and it's proven to do it correct. Last thing to keep in mind with the Columnstore index is that the implementation at the moment reads from the disk directly. So there is currently no caching layer. Why is that? Because we want to free up the second most, or maybe it depends on your workload node, possibly the most important resource for your workload, which is RAM. And the easiest way to free up RAM is to simply not use it, and therefore the Columnstore index is always read directly from disk. However, that also means that you should consider measuring your I/O subsystem and see that it can deliver a certain peak throughput for your data, because otherwise the data delivery to the tables to work on for with your joins and all your other operations might just take too long, and then it might look like that things are slowed down, whereas this is just a part of your system that's kicking in there. Okay, let's move on. That is a slide now where we briefly talk about for what you want to optimize. Do you want to optimize for disk usage or for CPU usage? And to motivate this a bit, we included two options for compressing your data. Actually, they are free, because you can also choose uncompressed, but that's rather unlikely to do. That's why we're not covering it here. So the interesting part is about the two compression options we have, and those are Z standard and LZ4. And on both of these compression mechanisms, you can define a compression level from 1 to 9, and the defaults here are always Z standard and compression level of 5. Now, the key question is, how does this behave when you're starting to vary this? So how does a Z standard compare to LZ4? And how does a compression level of 1 compare to a compression level of 9, also in terms of system resource usage? And for that, actually, we did a small experiment, and there's actually also a complete blog post about this topic. So if you want to get into more details, also with some more detailed analysis, then just read the blog post. The link is at the very bottom, and as Andy said, we are going to share the slides and the presentation, so this link is not lost, and you can also find it via our website. Now, when it comes to index creation, then we measured basically that if you're using Z standard, you get a super fast index creation if you choose the lowest compression level compared to LZ4. So this is saving ballpark 500 seconds here between those two. The medium size or default compression level of 5 is not that much more apart. And if you go to the highest compression level, actually, then Z-standard will take much, much longer. Actually, it turns around. So you're again, these roughly ballpark 500 seconds away in contrast to LZ4. However, looking at the sizes, that doesn't make much of a difference. And the base benchmark here, by the way, is again the TPCH data set with a terabyte of data in this case, and we compressed all the tables. And therefore, you get compression factors of up to 5.3 and as low as 3.5. Now, what does that mean? In the end, the default of Z-standard gives you basically the good middle between compression time and reduction factor, because this is like there's not so much space between 5.0 to 5.3, but that of course depends on your data set. However, on the raw numbers, it's like 250 gigabytes versus 234. So this difference is more marginal than taking this almost doubled runtime until your data is compressed. On LZ4, actually, this looks even a bit more shrinked, so we don't have that big of a span here. This is just a 0.2 and 0.1 to the next compression level, and therefore you can't do much wrong if you just choose the middle here, unless you really want to save time or you want to get the last bit out of LZ4 in terms of compression rate. So this is one side, and this is only highlighting now how long would it take me until my index is created and what kind of data savings I get. The other side of the picture is now, how long does it take me to run my workload? And for this experiment here, we were actually running the whole benchmark and with a reduced set of queries, actually, I have to say that as well. And if we now look into the first column, so this is a reference for Postgres here, and we reference this here because Postgres uncompressed can be, of course, measured with that workload. And we're roughly using, something about 8,700 seconds as in runtime. And if we look at the complete amount of data that's transferred, then we're talking about 15.6 terabytes here. So running the whole benchmark on native Postgres with all bells and whistles on takes 15.6 terabytes of data. Now let's look into Z-standard quickly. Middle again, because that's the default. We are reducing this to 1.1 terabytes of data transfer with the Columnstore index enabled, and the runtime reduces to about an 7 to 8x here in that case. However, if you look at the LZ4 numbers, then your data transfer goes slightly up, which is no surprise because the index just stores more data, right? So we're not having a compression level of 5, we have a compression level of 3.7, therefore you have to transfer more data. However, the runtime shrinks. Now, what does that mean? The standard compression, this very good compression ratio, comes at the expense of CPU. And this is just what you see in the runtime. So the amount of CPU time you save in terms of decompressing the data until it is ready straight away goes into your overall runtime of the workload. And this is basically also the second key decision you have to take, whether you want to have really low disk usage versus a lower CPU usage. So if you have these example 200 seconds to spare here on your CPU runtime for your workload, then you might want to opt for lower disk usage, or you just pick the exactly other way around. You opt for somewhat higher disk usage but lower runtime. Yeah, and this is actually something we were also a bit surprised of, and that's it's really helpful to get to this insight and to this data. As said, there's the complete blog post, which you can read up again with the same numbers. So I've just taken those numbers from the blog post, and there's also some deeper analysis on that. Okay, let's move on. Now, let's get a bit more into some more details, and also we do some hands-on now. Let's look at the part where this is made for, and this is big tables basically. Now, what do I mean by big? In the most straightforward case, big means the table is much larger than your index, than your RAM. Sorry. So, for example, you have 128 gigs of RAM. Your table is 300 gigs large. Then it's roughly 3 times. Now, if Postgres needs to scan that whole table, it's going to very likely fresh a lot of RAM or uses direct disk I/O, which makes total sense here because the moment you read something into RAM, it's very likely evicted the next moment, and therefore you are wasting resources. So let's assume it's going to read it directly. Then what we have seen in practice with the current Postgres versions available, you won't get something like beyond 2 gigabytes per second in terms of disk speed read if your disk can deliver that. Also, big means in that case, you possibly have a lot of indexes because you want to cover these cases we just talked earlier about, since it might be not really 100% clear what kind of index you need to satisfy your queries, and that can lead you into what we would refer to as index hell. So you have simply too many indexes to maintain. Now, I promised some hands-on. We have, as said, the TPCH dataset with 100 gigabytes of raw data. Now, those tables are likely going to fit in the RAM, but I'm going to show you that this is still beneficial in that case to even use the Columnstore index. So we take the orders table as an example. We are talking about 150 million rows here. And size-wise, this is a 20 gigabyte table. And with all the existing indexes on top, so we deployed the complete benchmark, the indexes are taking 10 gigabytes. So you have something like 30 gigabytes in total. Okay, so first things first, and I already did that in the background, creating the index. As said, we do the same thing what we promised before. We just use all the columns in the table. However, we skip that command column, that point here, and we are using the standard compression with a factor of 5 in compression, and that gives us about 20 gigabytes. So this is roughly the same size as the table in that case. Then we have to run vacuum analyze to build the index basically, and to also update your key statistics. And now we will start with querying that table, and I just picked a range-based query. So we are just going to select the average over the price for the year 1994. And I'm just going to execute this. And we will just run this once for now. And you will see a window popping up in a moment. There it is. So we move that to the right side. And switch that off here. And this is our query plan. And the interesting number here is that this took 4.5 seconds roughly. I'm just going to run this again because this was possibly not in the cache. However, given the size of the table, this might be in cache now. So I just run this again to see whether it changes anything in the runtime. And this is really a tiny change. So we're still at 4.5, 4.6 seconds, depending on how you round. Now I'm going to run this very same thing again with the Columnstore index. And here we are down to 1.3 seconds. Yeah, so this is roughly a speed up of 4x on the table. And this is also very consistent. Much like the other one where we are reading from RAM, we are reading from disk here now directly. I can repeat this multiple times. it stays at 1.3 seconds. Now, and what this little experiment shows us basically is that even if your table is in RAM, but you're reading still a large fraction of the table, and the table is rather large in that case, then the Columnstore, you will benefit from the Columnstore index basically. If, yeah, depending on the query in that case as well, of course, because what do we need to read here? We need to read 2 columns in total. And from a Columnstore index perspective, you just read those 2 columns. They are compressed. They need to be unpacked once. This then goes on your CPU, but that's it. Whereas here, I need to, for instance, scan the whole table, or I do have an index. Possibly Postgres decides that the index is not good enough, so it will maybe scan the whole table, and that is going to slow things down here. So that's one side. Now let's look into the extreme, in the other extreme, basically, and these are small tables. Now, what do I mean by small tables? Small tables means, in that case, they are going to definitely fit into RAM, and if you run a query, then it's unlikely that those tables are getting evicted, so that they are getting pushed out of RAM and you have to read them again. Why is this important? Because you want to have your tables in RAM all the time, ideally, to provide you the fastest possible access to that table. And just like the example before, we pick the table again. We have here the supplier table, which has 1,000,000 rows. And size-wise, we are at 170 megabytes. So that's a huge contrast to these 20 gigabytes from before. And there's a single index on, which is the primary key index with 21 megabytes. So those 2 sizes are very likely to fit in RAM completely. Maybe you have cold data, meaning you have to read it once, but once this whole thing is read, it is very likely to stay in RAM unless there are other things happening on your machine, but we just will assume this. Now, same thing again, we first create the Columnstore index. Again, I did that already using all the columns again. The Columnstore index here is 63 megabytes. So this is roughly half of the size of the table in that case. Now, first experiment again with the Columnstore index off. And I actually just do a complete table scan here, as you see. So I just select the complete supplier and calculate me the average account balance. And as you see on the right side, this goes really quick. This takes 70 milliseconds. And that's cached basically in RAM now completely. And very likely, it's very unlikely it's not going outside. Now we try with the Columnstore index enabled, and as you see, I just set this parameter to on here. And if I query this now, nothing changes. Why is that? Because the core system of Postgres knows that the reading of the Columnstore index on that table is more costly than it would use, let's say, the sequential scan we have here, the parasequential scan, or if there was an index, then the core system knows, of course, hey, I can use this index because this index is cached, and therefore this is going to be much more efficient than reading the complete columns. And just for the sake of the example and to show you like the difference in runtimes here, I now forced the usage of the Columnstore index first by, of course, enabling it again. And then we have to set a whole bunch of settings, like we have to disable bitmap scans, we have to disable index scans and sequential scans, just to be 100% sure that Postgres considers the Columnstore index as the scan type of choice. And I'm just going to run this again. This is the same query, and we are at 250 milliseconds here now. And this might be within your query SLA. So in other words, it does not harm you if you do this operation, but it also might harm you if you rely on having this return in these previously 60 milliseconds instead of 250. So this is something that can happen with tables that are too small. So when you choose to go with the Columnstore index, what we would recommend is go with your biggest tables first, keep everything else as it is, and then maybe change 1, 2, or 3 of your biggest tables at the Columnstore index there. Try a query, see how it goes, and from there on improve more. Okay, next example is point lookups. And here the key question is, again, what does a point lookup lead to? And it doesn't matter much whether this is now on a big or a small table. It of course matters in practice, but for this particular example here, it doesn't, because we do certain assumptions. And the assumptions here is that a point lookup is almost always using a index or a index only scan. So it either knows where the data is, or it can fetch the data directly from the index. And the fraction of the index it needs to access is very likely in RAM. And again, like with the small tables, it's unlikely to be evicted from RAM. And we use the orders table in this case because this is, as we've seen, a rather big table. If I do a complete table scan on that one, or even a range-based scan, which is spanning a whole year, then the Columnstore index is more beneficial. Here we do a point lookup, so we actually calculate the total price of all orders on a single day in 1995. And the first thing, again, is the Columnstore index disabled. And we see here what it does. It's actually doing a bitmap index scan. There is an index on the order date, and this takes us 130 milliseconds. Now, if we do the same thing with the Columnstore index, then the Columnstore index needs to read at least 2 columns. And depending on your I/O, and here it's important to consider then throughput and latency, this might take longer or not, depending on certain constraints. And as with the example before, because we learned that the cost system plays a very important role in choosing the access path to the table, we again disabled all these built-in scans like the bitmap scan, the index scan, and the sequential scan to ensure that the column store is used. So we have 130 milliseconds originally. Just going to run this again here, and we're at 770 milliseconds. So it's not that bad. It's still really fast, basically. If you consider, or if you aim to sub-second, then this is really fast, a really fast returning query here. Not necessarily for the OLTP folks amongst us, because really fast means there are maybe tens of seconds, even less. But the point again is here, the cost system helps you to make that decision that you see, because I had to disable a bunch of things. Plus, if you have to do a lot of point lookups, you might want to consider to not use the Columnstore index in that case, because it simply has to read then too much data. Okay, next one is how to keep the index up to date automatically. So we have seen before that I always added the vacuum analyze to it to build it and to put the correct statistics into the system. However, as you know, there's auto vacuum in Postgres, and auto vacuum helps you on this one as well. It just needs to be configured correctly. Now, for the following experiment, I choose a rather aggressive configuration. So I set the scale factors to 0 on both ends and the thresholds to 1. So the moment one tuple is updated or deleted, it's going to run vacuum analyze basically. And I set the nap time to a millisecond to just have it kick in really quickly with a high cost limit to spend as much resources as it allows here with the setting of 5,000 onto the operation. And like, because I watched this a bit, I set also the min duration to 250 milliseconds to just see some action there going on. So this is the base configuration of auto vacuum in this case. And of course, this is just an experiment. So for real world examples, your thresholds might be much larger, in the hundreds or the thousands even, plus you might want to consider scale factor depending on your workload. Oops, sorry. So now what we're going to do is, just skip one. We are going to prepare some data. So this I'm going to run, won't take that long, just I think 4 seconds or so. So we create us a new table, which I called new data here. New data has 4 columns, an ID, some random value, a Boolean flag, and a random string. And I'm also creating a Columnstore index on it over just all these 4 columns. This time I'm just including the comment for the sake of sizing. We will see this in a moment. And I'm vacuum analyzing that once, just to ensure that the index is built and that the statistics are there. And we inserted 100,000 rows here. Now, we are doing the following. We are going to simulate a workload that's ingesting data into the table, and then it calls, it updates exactly 1 row to just trigger the auto vacuum, basically. And then right away, we are going to run a query. And that query then will show how much the index is used and that it is basically updated. And to just show you the semantics first, I'm going to run this query alone. And this is just calculating the averages and the sum over the values over the whole table. Yeah. So now we have the Columnstore index here. And if you look at the output for a moment, I'm just going to switch over here. You see these 2 statements where it says heap blocks and index blocks. And what this tells you is how much data comes from where. If it says heap blocks, it scans the table directly. If it says index blocks, it goes to the Columnstore index. Now, why does this vary? Because if you add data to the table, then the index takes blocks and combines them into a single new block because of this columnar storage format. And to make this operation useful, you have to surpass a certain threshold. So basically, the 100,000 rows we inserted, they cause the index to be partially created as the index itself, and there is a bit of leftover on the table, and that's why you see those 2 values. However, for the experiment we're doing now, it's important that over time, so whenever I insert new data, the amount of index blocks grows. If it would not grow, then that means that your index is not updated, and that makes operations slow. And that's something we're going to look at now. So I'm just running the complete query now here, and I reduce this also to 4 workers to get the output a bit more condensed. And let's just run this. So we did now 1 run, and the first thing we see is it called basically the update 1 here. We don't see the insert because I'm returning the result from there, but we inserted 25,000 rows. And interestingly, heap blocks is growing to 1407 and index blocks is 0, meaning we suddenly read from the table, not from the index any longer. And I'm just going to run this again. And now it changed again because auto vacuum kicked in between and was rewriting some of those index blocks. And actually that is part of this update mechanism, because an update can cause to go into a different page. And if that page is in the index at that point, then it needs to remove it from the index and re-edit later. So if I call this again, we see how the heap blocks are growing, the index blocks are staying stable. Why is that? Because we did not met the critical limit yet, where it makes sense to actually combine combine heap blocks into index blocks. So I'm just going to run this again. Yeah, still not there because we're only doing 25,000 rows. 1 more. There we go. Yeah. And now it combined quite a lot of heap blocks into index blocks, and by that also shrink the data. So meaning you read 1 index block, you get much more data suddenly. Yeah, and I can just repeat this experiment now, and I'm not doing anything else. So as you see, I'm not running manual vacuum analyze or the like. It's just auto vacuum doing its job in the background, taking on my freshly inserted data and just updating the index for me. Yeah. So we are still not on the critical limit here, but now we are. And again, we have this quite large reduction, which is roughly a factor of 3 of heap blocks to index blocks, making the whole operation, the whole query operation in the end more efficient. So that's how auto vacuum works. The key here is to really configure it correctly and possibly or very likely to watch your log system to just ensure that this runs like it should. Okay, last slide for today. Typical case, you have OLTP, you want to have analytics on top, and now you're considering the Columnstore index. That's really good, that's a wise choice. But the main question is, do you want to put this on your server or not? Or maybe do you want to have a second instance? Now, simple rule of thumb, if your server has capacity left over because you're, for instance, not driving it to the limit with your OLTP workload, then it's fairly safe to just add the Columnstore index. And then, as said, keep your auto vacuum enabled, configure it correctly, and have the index updated in the background automatically. And then you can run analytics with the help of the Columnstore index on your existing workload. Or if you are out of capacity because, for instance, your OLTP workload is consuming close to 80 or 90% of the resources of your system, you want to consider replication. And small marketing hint: if you're an Amazon RDS, where you unfortunately can't load our extension, then we have a nice product for you, which is called PG Nitrous, and we have a blog post talking about how to replicate from Amazon RDS to PG Nitrous, and then you also get analytics again on a single source of truth, essentially, because most simplistic, your replication is going to just mirror your data, or you can also choose to transform your data in between. And having said that, I'm saying thank you, and I hand back to Andy.
Thank you very much. Okay, thank you all for staying with us, a little over schedule. Appreciate you joining us today. Hopefully you found the Sebastian's knowledge useful and informative. And we look forward to seeing you online in future events. Thanks very much. Bye-bye.